Best explanation of linear regression. Machine learning algorithm. What is the difference between machine learning and just an if-else ladder? If there is a labeled dataset, why can't we just put out a code saying, hey, if x1 equals this, x2 equals this, x3 equals this, xn equals this, then output y equals this and add such many more cases for all data points, and it would work as good as machine learning. The point is, in such a hard-coded fashion, if you give the series of if-else cases a data point from outside the labeled dataset, it won't be able to give you an output. Thus, it cannot predict. It has only memorized previous cases. That is why we need to train a model. The model should be able to derive outputs for new cases or data points that it has not encountered before. To get such a solution for a dataset that is continuous variable in the output/target column, regression is the tool. Let's consider a single featured dataset. In case the number of features increase, the plot would be beyond 2D. The image on left shows the labeled dataset, y plotted against x, for which we want to get such a solution. And the image on right is the solution. It's a line that approximates the distribution of points. Note that now for any value in the world, be it from the labeled dataset or a new data, i.e. for any x, using the line, you can find its corresponding y. The line can be expanded in both directions, therefore literally for any real number in x you can get a prediction. Therefore this line, y equals mx plus c, simply derived from previous data, is the solution to predict for new data, and this is linear regression. Now the question is, there would be many lines that would look as good to approximate the distribution. How would we get the correct line for the purpose? Intuitively, a correct line would pass through as close as possible to the points in the distribution. That is to say, the sum of the distances, measured along y-axis, between the line and the points in the distribution would be the least for the correct line. If we consider this as loss function, L, that should be minimized. We start with any line, combination of m and c, at random. Our aim is to get to the correct line for approximating the distribution. The only way we can change this line is by changing m, slope, or changing c, intercept. How do we change m or c? We have a m and a c now. We get new m by m underscore new equals m underscore old minus learning rate underscore, which is a constant, times delta L, delta m underscore old. Dot, L equals y minus m underscore old x plus c squared. Therefore, delta L, delta m underscore old equals minus 2, y minus m underscore old x plus c, x, from which we can easily get to a number putting the corresponding values. Thus we get a new m by m underscore old minus that number. This is true for c as well. C underscore new equals c underscore old minus learning rate underscore, which is a constant, times delta L, delta c underscore old, where delta L, delta c underscore old equals minus 2, y minus mx plus c underscore old, and we can get a new c. We keep on repeating this process with the m or c that we get, which now becomes old m, old c, and we try get a newer m or c. Thus we keep on getting different lines. And our search ends only when m or c no more updates, i.e. when delta L, delta m underscore old, or delta L, delta c underscore old, equals 0. Note that delta L, delta m underscore old, or delta L, delta c underscore old, equals 0 is also a condition for loss to be minimum. Therefore throughout this process at each new m or c, loss had also been decreasing, and we reach the correct line only when loss is at minimum. Lastly, note that m or c is increasing at each step and not decreasing. This is because in getting new m by m underscore old minus that number starts with a negative sign. Negative, negative, positive. Same for c.